workbook, and everybody has a workbook now, right?
Yes.
Okay, cool. It states that two events are independent events if the occurrence of one event does not affect the occurrence of the other event. Then they are independent events. For example, rolling a 1 on a number cube and choosing an ace at random from a deck of cards. What I roll on the die does not affect what I draw. Independent events. Make sense? So you can kind of think about it, use your common sense, think about it, but we can also test it mathematically. If two events A and B are independent events, then the fact that event B has occurred does not affect the probability of A. In other words, for independent events A and B, the probability of A is going to be the same as the probability of A given that B happened. That probability will be equivalent. And we're going to look at some examples to make that make sense. Okay? Now there's some stuff at the bottom of the page we're going to come back to in just a second. So let's flip over to page 442. Alright, on 442, it says you can use a tree diagram to help you understand the formula for probability of independent events. For example, consider tossing two coins. The outcome of one does not affect the outcome of the other, so the events are independent.
That makes sense.
Okay, so what I flip on the first coin does not affect that second coin.
So
Make sense?
It has to be like two different ones.
It could be the same coin, and we could just flip it twice. But what I flipped the first time
It doesn't affect
doesn't
the
matter.
outcome.
Yeah,
The
doesn't
probability is still
affect.
50-50.
Yeah. Alright, so the tree diagram shows the probability of a coin landing heads up on both tosses is 1/4. So heads and then heads, that's this branch. That is one branch out of the 4 branches. So do you see it's 1/4? Okay? The probability is simply the product of the probabilities of the coin landing on heads on each individual toss. Now let me write this out. The probability of heads and heads, we counted from here, was 1 out of the 4 possibilities in our tree diagram. Is that equivalent to the probability of tossing heads once and then tossing heads again? Yes. And because this is true, A and B are independent events. If and only if. When you guys did proofs, did y'all use the letters IFF as an abbreviation for if and only if? No? Okay. Well, maybe when we pick up some proofs when we do the circle unit, we'll revisit that. So what do? To find the probability of A and B, it's the probability of A times the probability of B if the events are independent. Okay, so here we have a fair spinner. And in math world, we're going to assume it's a fair spinner, it's a fair die, it's a fair coin. Nothing's rigged in here. Okay? So, you spin the spinner to the right 2 times. What is the probability that you spin an even number on the first spin, followed by an odd number on the second spin? So we want the probability of even and then an odd, right? Are these events independent? Does what I spin on the first one affect what I'll spin on the second one? No, they are independent. So what I should be able to do is the probability of even times the probability of odd, because my events are independent. So the probability of doing an even followed by an odd would be, how many even numbers are there? 3. Out of how many spaces? 8. Times how many odd numbers are there? Out of how many spaces? So the probability of an even followed by an odd would be 15/64.
You multiply across.
You would, yes. Probability of an even then an odd. Okay, so independent, we just multiply. Got it? Okay, let's talk about one thing you're going to look for. You don't have to go to this page, but on page 442, 47, it gives us some problems. This one has a bag of marbles. We're selecting a marble, but then we're putting it back. If we put it back, if there is replacement, then we have independent events. But if we pulled a marble and did not put it back, it's dependent.
Because then there's one
Because
fewer.
the first one does affect.
Yeah, because there's one fewer, so then there's less probability. Okay, that's fine.
Okay? So, that's one word you can be looking for. Alright, so now we're going to look at that second thing it talked about, the probability of A given B.
That's right now.
Is the probability of A equal to the probability of A given that B occurred? This bar is given. That's what that bar means. Given that B occurred. So here's a chart. We're back on that page 441 that we skipped a second ago. And it says an airport employee collects data on 180 random flights at the airport. The data is shown in this two-way table. Is a late arrival independent of a flight being an international flight? If they are independent, this is also true. The probability of A is going to be the same as the probability of A given B occurred. If they're independent, we should get the same thing. Okay, so let's take a look. To find the probability of A, first note that there are 180 flights. How many of those 180 were late? 18. 18. Okay, so that would be 18 out of 180, which is 1/10. Okay, now we're going to look at this probability, the probability of A given B occurred. First note that there are a total of how many international flights? Because it's given that it's an international flight.
60.
Do y'all remember doing two-way tables and when we had the given part? Okay, so it's 60. Of those flights, how many were late? 6. So the probability that it's late, given that it's international, is 6 out of 60, which is 1/10. Are they the same? Yes. So, a late arrival we would consider independent of it being international because the probability of A, 1/10, is the same as the probability of A given B. Does that make sense?
Yeah.
And that is one way to prove independence. Yes, sir.
Our page is different.
No, mine isn't.
It says on-time flights. I feel like I'm looking, yeah, oh, maybe I'm looking, my bad.
Okay, shoot. All right. There's another one on 443. Is that the one you were looking at?
Yeah, that was.
Yeah.
Okay. Okay. Okay, so this one, showing that events are independent. So we looked at one way, now let's look at the other. Alright, to find A, B, and the probability of A and B, note that there are a total of, there's still how many flights?
180.
180, okay. 162, we're on time. So the probability of A would be 162 out of 180, which I'll go ahead and tell you reduces to 9/10. Okay, there are 120 domestic, so 120 out of 180, you can reduce that one. 2/3. Okay, the next one, how many are on-time domestic flights? 108. So this would be 108 out of 180 is 3/5. So the probability of A and the probability of B. The probability of A was 9/10, and the probability of B is 2/3. So let's do some magic canceling. 2 goes into 10 5 times. 3 goes into 9 3 times. 3/5. Is that the same as A and B?
Yes.
Okay, that's my other way. The probability of A and B is equal to the probability of A times the probability of B. They are independent. That's how we can prove it mathematically. what could I use instead of this word? Could I use that symbol?
Yep.
Yes. Okay. Alright. Dependent. This is when they do effect. So if we pull that marble and don't put it back, we're changing our total. Okay? So, to find, gives us a conditional probability. A conditional when they are dependent. Okay? And let's see what the important parts are here. So here is one of our formulas for conditional probability. The probability of B given A is the probability of A and B divided by the probability of A. And I usually don't have to do that much math to figure it out. So if we flip over to 446, let's look at number 2.
2. That does not look like that.
Okay.
Good afternoon, everyone. We have one afternoon announcement. Cross-country practice is canceled for today. Thank you.
Potential.
Okay. All right. We are drawing something and we're putting it aside. We are not putting it back. Independent, dependent.
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 Not putting it back.
So, what is the probability that you choose a bottle of apple juice followed by a bottle of grape juice? Well, the first draw is 6 out of 14. Because 6 are apple out of the total of 14.
Okay.
Now, the second one, we want grape. How many grapes are there? 8. But now, how many juice boxes are there? 13. Okay? So do we see how we find the probability of apple and grape is going to be different? Because it's the probability of apple times the probability of grape given that we drew what? An apple. So this is a conditional probability. So it's the probability of apple times the probability of grape given that we drew an apple. And that's how you calculate it. So with a conditional, those denominators are changing, aren't they? Because we're not putting something back. There was an effect. Okay. They really came over the announcements pretty early, didn't they? I've got 4 more minutes. I felt rushed there for a second. Okay. Here we have a bag with 12 blue, 12 red, 20 green. A green, then a blue are chosen with replacement. With replacement, independent or dependent? Independent. 2 blue are chosen without replacement. Dependent. Okay, so that's the big thing. All right, now, this is going to be on the notes. This is the part that's hard. It's the symbols. Okay? It is the symbols. So this is A and B, right?
Right.
Is the probability of A times the probability of B.
And that is what?
Okay?
Joint probability.
But this is also going to be true if there are independent events. The probability of A is going to equal the probability of A given B happened. That's going to be an equivalent statement. Or the probability of B is equal to the probability of B given A. When they are independent, these things must be true. Okay? So this is one way to prove it. This is another way to prove it. All right. Now, when they are dependent, a different story. Okay? So dependent, this is our formula. We have to do the probability of the first one times the probability of the second one given the first one occurred. And our denominator is going to change then.
So if it was like, as you did 14, it would be 13.
Okay, so all these notes will be up on my notes page. It's the textbook. I'm handing out the worksheet now. Since you don't have the textbook in your possession yet.
Oh, it's just the worksheet? Okay.